with the concept, it makes it easier for you to implement. If you weren't there for the previous session where we did data structures introduction, where they were talking about linked lists and arrays, you'll see linked lists and arrays build up these stacks and queues. But if you weren't there, we'll share the link with Charlie, no pressure. So first we'll heavily focus on the concept, because once we understand the concept, it makes things easy for you, even the implementation, because you have an idea inside your head. Yeah, Samson will take you guys first, then I'll just add one or two, three things that there from what I see ama what I feel that hakuguzia vizuri, and then we'll have a question and answer session tukimalizia. Anyways, Samson, I hand the mic back to you.
Okay, so thank you. So, as a friend of mine used to tell me, you cannot build a chair if you do not know how the end product is supposed to look like. So, you cannot start, merging a wood piece by piece with another piece without you knowing like entirely how the entire picture would look like. So, that is what we'll be focusing on mostly today. So, we're just going to talk about stacks and queues, and then later in another session, we're going to cover more. So, stacks and queues, I think, okay, sorry. So, just a minute. Just I didn't. Sijui mbona inahama. So the topics we are going to cover. So currently, when we're covering stacks and queues, we have a lot we can cover, but we aim for this session to cover only 30 to 45 minutes, and hoping that we're going to to explain the core concepts surrounding stacks and queues. So in the introduction, we're going to cover a basic explanation of why we need data structures and what data structures are, and then we're going to cover stacks and queues, talk about the real life examples and applications of stacks and queues, the key characteristics and operations, and then we're going to cover like now the key characteristics maybe of stacks. We're going to cover maybe push operations, pop, what is peak in stacks, if you what other thing you can do like checking if a stack is empty, the whole concept of last in first out in stacks, and then the application of stacks maybe in things like function calls, recursion, undo functionalities in text editors, browsers, and other things where stacks apply. And then we're going to cover queues, uh, the basic operations about queues. And then next, we're going to cover like the comparison between stacks and queues, and when to use like whatever data structure you're supposed to use when when to use a stack and when to use a queue. And then beyond that, we can cover like more advanced concepts. I want to cover something about the DFS and BFS, but apparently maybe some of you don't know about graphs and those things. So apparently next session we're going to be covering about graphs, and I hope the person will be covering that will talk you will walk you through DFS and BFS. But we're going to talk about implementing stacks and queues using the other data structures. That is to mean we can implement queues using stacks, and we can also implement stacks using queues. I mean, that is cool. Then we're going to talk about efficiency, that is time complexity and space complexities, because when it comes to computers, you really need to focus mainly on building systems that run fast for one, and do not occupy like the entire memory. So you don't want to be running an application and then all of a sudden it's either slow or you're running out of memory. So, and then we're gonna also touch maybe something on a couple of interviews problems that you might encounter that are really based on stacks and queues. Some of them include the ones I've listed below. and then we can talk about the common pitfalls that people should avoid when implementing stacks and queues, be it in interviews or in any other field, wherever you'll be implementing stacks and queues. So just to reiterate, mostly whenever you're working in real life projects, you mostly won't implement maybe stacks and queues, but rather you will use mostly maybe libraries that have already implemented stacks and queues inside them to maybe improve on efficiency and other things. But the whole idea of you learning stacks and queues is so that whenever you're using such libraries or anything, or you want to custom build your own stack or queue or any functionality that should implement this, you can basically do that. So I won't basically introduce much on data structures because ideally that is what is written there. So data structures and algorithm. Why do you need data structures and algorithm? This is a key point in when it comes to data structures and algorithm. So abstraction, you hiding data from other people so that people who are unauthorized within a system cannot know like how you really implemented something. So to give an example, maybe some of you have used something like the common printf, or not, or print function in Python. So ideally, we all use that, but in as much as you've ever implemented that in your C, maybe ALX curriculum, in most cases, nobody knows how it has been implemented. So you basically just write printf or console.log, and then ideally you print that. So the whole idea of hiding data behind there so that somebody can just call maybe a function or a method, and then it works. So that is what we call abstraction. Then reusability. So you don't necessarily need to keep building the same thing whenever you're implementing like another thing. So ideally, what you can do is you can build one maybe data structure, and then whenever you want to use a similar data structure as that, you can just call it. So for those who have used maybe Python, to give an example, whenever you're building things like lists and such things, I mean, they've already been implemented somewhere else. All you have to do is maybe call that class, if I'm talking the from a point of maybe more concrete languages like Java or C sharp. Maybe whenever you're calling a class for maybe an array, you just call it from somewhere else, and you don't need to keep implementing it. The reusability purpose, like a function. Scalability. So whenever you're building systems, you need to build them when well at the back of your mind, you thinking that in future this system is going to be able to accommodate maybe 10 million people, and then in future you need to be able to handle like now 10 billion people. So how do you build a system that you can, you know, build maybe use that effectively without you keeping or without the system being down all the time or anything. So abstract data structures. So abstract data are high-level models that define the behavior of data and operations performed on the data without specifying the implementation details. So the whole concept of abstract data structures come from the keyword abstraction. So I'm going to talk about just the characteristics. So encapsulation, hiding the internal details, that is part of abstraction. Behavior specifications, you define the behavior of data. So what is needed in that data, what will that thing do? Like whenever you're building linked list, you have like the data itself, you have like the next pointer. So I mean, the next pointer is supposed to point to that one. That is like the whole concept of abstraction in data structures. So when it comes to, I'm not going to repeat again on data abstraction. It is almost the same concept. Uh, Client perspective. So client perspective is also like the same as data abstraction. You just hide whatever is out there. The client doesn't really necessarily need to know like what is happening. All they need to do is interact with the system. Uh, you guys use systems like literally right now we're using a system, and nobody knows how it was implemented. But what I'm doing is just pressing next, and as long as it works, nobody cares. So that is the whole idea behind client perspective. So these are examples of common data structures. So there are stacks, which we're going to talk about. There are queues, which we're also going to talk about. And then there are lists. So lists are almost similar to arrays, depending on the language you're using to implement either one. So when it comes to C, when you're using array, it's not similar to Python array and list. So I'm sure you can Google that somewhere. There are trees and graphs from how they sound a tree from one point going downwards with branches the same. I'm sure these ones are going to be covered more in depth in the next session. The whole idea is to explain what common data types there are. So basically now what queues and stacks are. So without uh, thinking much, I'm going to give you a small example and then hope that it's going to drive the whole point of queues and stacks home. So when it comes to stacks, the underlying concept is LIFO. So basically, wherever you enter, so basically LIFO means last in, first out. So wherever you enter last is what you're gonna get first. So in this scenario, so say you have something like a stack of dishes. So ideally, a stack of plates. Let's use plates. So you have so many plates, and then you stack them on top of each other. So, assuming you are starting on a bare uh, a table, so you put in the first plate, and then you go ahead and put another plate on top of that plate. You put another plate continuously on top of that plate until now you have like a stack of 10 dishes. So the last plate that you just put on top there, that is what you're gonna get first. So if you want to take a dish, a plate, you're gonna start with the one at the top. So the same concept applies. The last thing that has been entered into that data structure is the first thing that is going to be extracted. The first thing that was, hello,
Samson,
okay,
let me help them with a different example kidogo. Eh?
okay, go ahead.
A good example ni when you go to the supermarket, alafu let's say you've gone to buy crisps or something. Eh? You go and pick that crepes that is looking at you, that first one, you take it. But when they were arranging those crepes, the first ones were put zikapoko nyuma, alafu za kwanza za mwisho ndio the ones you see at the front. That's first in, first out. That's another concept of that one.
Yeah, so
Hiyo
yeah,
example ni mbaya, lakini inaeleweka but ni mbaya.
it's not actually bad because when people are arranging things wanaanzanga huko nyuma and then wanakuja mbele, and when people are buying things wataanza kuchukua zenye ziko mbele wakienda. But either way, I believe the point has been driven home. So if that example doesn't go with you, you can go with the first one where we have a stack of plates. So hizo plates, whenever you are arranging them, unaziekelea on top of each other, and then whenever you're picking them, apparently you won't start with the bottom one unless kuna watu weird, so they can just start from the bottom. But in this scenario, let's start from the top. Ukianza kuchukua, you just pick the one at the top, and then you keep moving on until ziishe. So that is how it works. And then when it comes to queues, so queues is basically like the queue, a normal queue, or whenever you go to a bank. Whenever you go to a bank, whenever you get your ticket, so your ticket will be after the one after the ticket. Your ticket number will be after the ticket number of the person who came before you. So apparently, if maybe somebody like Joshua comes at the first one, so he's gonna be in the first one in line, and then another person comes behind him, so continuously until we have like a long queue for those who use kitu kama super metro. So the guy who came earlier ndo atakuwa served early. So the guy mwenye alifika wa kwanza ataingia kwa bus mapema, and then the guy mwenye alikuja wa mwisho ataingia wa mwisho. So that is the whole concept. If you come first you get served first. So that is the whole concept of queues. Anyone else anataka kupatia a more in-depth idea of what queues are? Okay, so if
Well,
nobody else,
the next best example apart from the one for Super Metro yenye umepeana ni when you go to the bank, see you get a ticket.
yes.
Every ticket wewe umekuwa kwa queue yako,
Mm-hmm.
be it you're depositing cash na withdraw, wewe uko kwa queue yako. Kama kuna mtu mbele yako, you won't be served up until that person has been served, ama alitolewa kwa queue, something of the sort.
Yes. So to put it in English and in a way nimeiandika, so a stack is a last in first out data structure, meaning that the element added is the first one to be removed. Okay, so I meant the last element added is the first one to be removed. So elements are added and removed from the top of the stack. So we shall cover that later. And in queues is first in, first out. Whatever comes in first gets served first. So let's go on next. So example use cases of stacks. So function call in stacks. For those who have done like more programming, you know something we call recursion. So recursion applies this principle. So you keep stacking things, and then you keep stacking functions, and then you pop those functions later. So I believe tunaweza ongea about recursion maybe at the end or maybe later kama time itakubali. Undo functionality. So most of you wanatumianga vitu kama word, and then after you've written something you need to undo it and then get back to wherever you were previously, or maybe VS Code or anything. So undo functionality uses stacks because it stacks things, and then it can undo, just pop the one at the top. Expression evaluation. So I don't want to talk about postfix notation. I don't know if most of you will understand this one. Or Sage, do you have a simple explanation I could explain easy nini postfix notation?
Not really. See, okay, can't say ni simple.
Okay.
So tusonge tu
So
alafu get time tutaiongelelea baadaye.
okay. Just let's tupite hiyo. So in queues, so print in queues, um, whenever you want to reach something like a printer in an office, so the one who sent a request to print first is their documents are gonna be printed first, and then in that order you send your documents to be printed. The printer is going to queue them and then print them in the order they came in. So breadth first search. So I'm not going to touch on that. So somebody is going to be touching on that next time. Task scheduling. So when your operating system is processing things, so it schedules the tasks, yeah, based on how they came in. So if you send this one first, it's going to process that and then move on to the next. It's like whenever you're coding. So whenever the system is trying to execute your code in Anzanga from the top, executing line by line, line by line, line by line until ifike huko chini. So that is implementation ya queue. So key characteristics and the operations. So in stacks, some of the things you can do when you're using the stack data structure. So you can push, that is, it means you can add a new element into the stack because it is a data structure. Pop, you can remove the top element from the stack. So you can just remove an element from the top of the stack, and then pick. You can just have a pick. Look, what is at the top of that element. So ideally, stacks they deal with the one at the topmost element. So ideally, you're gonna be adding elements at the top. You're gonna be removing elements at the top. You're gonna be checking or picking an element at the top. You can also check if the stack is empty, because if it doesn't have any other element, I mean, it's empty. Sawa sawa. When it comes to implementation, you can implement a stack using a linked list or an array, or you can use any other data structures like queues. But today we're going to focus on the simple part on implementing stacks using arrays and linked list. And then later I'm going to show you how to implement a stack using a queue. And then when it comes to a queue, I'll show you how to implement a queue using a stack. Interesting. So implementing a stack is an array. So I'm a little bit conflicted. I am thinking of either showing you like a diagrammatical representation or showing you the code. But the whole idea is you guys know what arrays are. It is a block of contiguous memories. So apparently you have a couple of yeah. So this is apparently this is something a contiguous block of memory. So you can call this an array. So apparently, when you create an array, whenever you're accessing elements from an array, you start maybe it starts its counting from index 0 to whatever index. I can say index n. So the first, in order for you to access the first element in an array, you use index 0. So index 0 covers for you accessing the first element in an array, and then continuously. So right here I have a very good example of me showing you how to insert things in a stack using an array. So apparently what you do is basically you have your array. So what you have to do is now you can keep appending data into that. Whenever you're appending things into an array, you're basically entering that data at the end of that array. So now if the array is empty and then I append something like 12, so apparently it's going to occupy at index 0, and then I append another item like 08, then it covers the next one at index 1. I append 21, that whatever is continuously as I'm appending them, uh, I'm gonna reach to maybe at the end of that wherever I am, the items that I have. So if I want to remove them, rather than me starting from index 0, I start now from the last element that I just entered last. So apparently from this example that we have, we just entered 40. So 40 was the last element. So if I want to pop something from a stack, I'm going to remove 40. So if I remove 40, I'll now have like now 18, that 33, 21, 08, and 21. If I pop 18, I just now remain with 33. If I decide to do something like pick, so assuming that we still have like the original data structure starting from 40, 18, 33, 21, 08, and 12, and I want to pick. So apparently, I won't be removing 40 from the data structure. It will still be there, but I will just have a pick. Just look at what is there at the top of that stack. So basically, in simple terms, that is the basic implementation of stacks using arrays. Does somebody has any question? Any
So,
question? Yeah,
let me ask you a question.
go ahead.
Supposedly, we have the whole stack filled with our data.
Mm-hmm.
Let's use the one that you have.
Okay.
Can we pick at number 33 when we have 18 and 40 on top of it?
Okay, so apparently it is possible for you to check maybe the third element that was inserted, because ideally you can loop through an array, right? But that is not the implementation of a stack. So when you're talking about picking in a stack, you're just looking at what is at the top of the stack.
Yeah, that's good.
Okay, so basically that is the whole implementation of. So I'm trying to give you the mental picture of how you input these things, so that uh, if you know like what you are supposed to expect at the end of it all, then that makes it simple for you to know where to start to code. But apparently I show you the code implementation for it. So I'm going to go next to implementing a stack using a linked list. Okay, let's go ahead. So these are some of the operations in a stack. I'm just going to skip that and then go to implementing a stack using a linked list. So apparently what is happening, if you remember us learning linked list previously, So you create a node, and then it has a data, then it has a next value. So apparently, when you create the head node and then you create the first node, so the head node is going to be pointing at the first node that you implemented. So if you insert, so whenever you're inserting something in a stack using the implementation of a linked list, all the time you're going to be inserting that element or that node at the beginning of a linked list. So just to show you like what I mean, so say I have like an already defined stack like this one. So I have node 1, node 2, node 3. So for you to have an efficient time complexity and maybe space complexity, you don't have to recursively go through node 1, node 2, node 3, and then enter a new node at the end of a node. The best implementation for that is for you to insert a new node at the beginning of that linked list. So you have your data structure and you want to insert, so you create a new node and then you merge it to like the previous node that was the head node, the the first node, and then the head node now points to the new node that you have created. I don't know if this is a little bit complex. Are you understanding what I'm saying, Sage?
So kama kuna mtu mwenye hajaelewa what Samson has just said, yeah. For the linked list, we talked about it, the linked list has a value and it has a pointer that points towards the next node. It'll actually show you a code for that implementation, and we did it in the previous session. So for linked lists, it's usually easy than traversing through. Traversing through is going through the linked list, like you go for the first, second to the last node, to the nth node. It's easy for you to implement a stack for a linked list by adding a node at the top at the first one instead of going through then adding it at the final one. Because looking at it, since you already have the head node pointing to the next one, and you don't have the last node pointing to something because it's pointing towards null. You can't add something at the null. You'd rather you add it at the head node. Yeah. So you just change the head node and you add you put the next for the node that you're adding to point to the first node. That makes life simple for you while you're implementing it. Does
Okay.
anyone have a question after that explanation?
Okay.
Then I
So
think we're
yeah.
kuendelea.
So I'm assuming nobody akona swali. So I'm just going to show you some code for implementing stacks using a linked list and an array. So this is us implementing a stack using an array. So apparently, because an array is a block of contiguous memory, for you to maybe if you have like 30 elements and you want to insert them, it is wise for you to decide rather to decide like uh, I need a space that is equivalent to 30 elements, so I can put in 30 elements. So that is where like now you define like the max size of your stack, so that you cannot like add more than 30 elements, but you have like the power to define like how much space you want to allocate, but you cannot allocate like the entire memory. If you want to recreate this stack and say like in future you maybe right now you allocate like you need a space for 30 elements, and then after a while you realize that you need a space for 50 elements. So what you're going to do is you're going to create another uh, stack which will have 50 elements, which can uh, carry like 50 elements, and then you're going to copy everything that you had in your previous stack, and then you put it there like the 30 ones, and then now you add your 20 ones, and then now you have your 50 ones. So it is a little bit can I say unorthodox? Eh?
Acha nikukatize kidogo, yeah.
Okay, go ahead.
So this is because Nimona Kendi has said she has not understood. Yeah.
Oh, sorry, I didn't see that.
So put it just for you that image on the slides of the node and what that one.
Can
So
I? Okay, this one.
yeah.
Okay, go ahead.
So Kindi, we were talking about linked lists. So assume that one head, that's the head node for the linked list. Then there's the first, second, and the third node. Yeah. Kwa that whole node, yeah, traversing, what we're trying to do with stacks and queues, as much as we haven't talked about time complexity and space complexity, which is essential kwa hizi vitu zote, because at the end of the day, in this day and age, we want things to happen fast and we don't want them to consume a lot of space. So for us not to consume a lot of space and to make things fast, how can we implement something, maybe add something to a stack with this one? So let's take that head node. Is it easier for us to go to change if the head node is pointing the next or the first node? Or is it easy for us to go through that whole linked list till the third node, then change that next at at the final one to point towards our new node? Which one of the two is easier? Ideally, it's the first one, right? So kama ni rahisi kuchange the head node kupoint hii node mpya yenye tunataka kuweka kwa list, na hii itaturahisishia time, na itatureducia resources kwa ajili the number of loops zenye mtu ataweka going through the first to the last, so that we can add a node ya huko mwisho, na just changing the pointer ya head to the first node, that will be easier, it will consume less resources. I hope you may make a bit more sense than the first explanation, right?
Hebu nikuulize,
Yeah.
Uliza.
so basically kuadd nini kitu kwa hiyo stack juu
Mm-hmm.
ni kama kuadd a new node alafu hiyo new node unaichange inakuwa head.
Exactly.
Ah, ni sawa.
So yeah, the whole idea ni because tuseme saizi
Mm,
uko na linked list na iko na a million elements, si ndio? If you want to add
ndio.
at if you want to add uko mwisho, you'll have to first of all traverse from the head mpaka ufike ya mwisho, and then now you add there. You see, umeongeza like time complexity because first of all your program has to go through all those nodes and then now decide like imefika ya mwisho, so now I can add now at the end one, si ndio? But it is much easier if you just change the first node to be there, like rather than you traversing, just making the head node. Is it
Okay.
iko poa mover?
Iko sawa.
Okay,
Iko
so
fiti.
okay.
Mambo discussion every time and out, every time and out.
Sijasikia kenye umesema. Okay, sijasikia kenye amesema, nimesikia tu every time and out. So nilikuwa na wa explainia sasa now like the implementation, nikuonyesha the implementation of stacks using linked list. Sawa sawa. So I'm trying to explain now like the base concept, and then now we can now move fast through the other concepts. So the when you're implementing stacks using a linked list, not a linked list, an array, because an array is a block of contiguous memory. Now whenever you execute something iko kwa array, the next memory yenye haija executiwa, the computer uses it to execute another variable or another thing. So for you to avoid the whole thing, you have to first of all specify like a certain block. Useme like for 30 elements I want to store in this memory, so the computer will create an array of that size, and then you start now inserting things in that array. So that is why now, right, whenever you are starting this stack, so in the init method I have the max size. So whenever I call this class stack, I'm going to be passing the maximum size of the array I want to create, and then I'm going to create an array of that size. So that is like just an empty array multiplied by that size. It's going to be creating like a memory of that size. Now, the top of the stack will always be -1 to mean like you have an array, and then an array at -1 basically means that there is nothing there to get if it is empty. So that is to check if it is empty. To check if it is empty, you just check if the top is -1. If the top is -1, that array is empty. If the top is something like 2, because assuming now I have an empty array, it is basically -1. If I add one element and then I add 1, so it is going to be 0. So array at 0, you have an element basically. If I add another element and then we have the top being 2, so array at 1 now, because 0 plus 1 is 1. Now the array at the second element is, array at 1, so you get that way. I hope you're getting the concept of why I'm using -1. So to determine if a stack is full, you just check if the top element is equals to maximum size -1. So why maximum size -1? So say you have 30, so you pass your maximum size as 30, sindio? So and an array inaanzanga count from index 0, sawa sawa. So meaning that if you want to have 30, you just count from 0 to 29. So that is why we have 30 minus 1, so that we can get to 29, because the top will count up to 29 if you set the max size to be 30. So if they are equal, then the stack is full. So to push an array, you just check first of all if it is full. If it is full, you just raise an exception, the stack overflow. So stack overflow meaning that unataka kuweka kitu imwagike, which doesn't make sense. If it is not, you increment the top. If initially the top was maybe -1, so you implement 1, and then because it is now stuck at 0, you can now it is now array at 0. Now array at 0 is going to be now equal to that data, so you keep incrementing that. So popping is removing that a data from the top of the stack. So apparently, as you are implementing a stack, it's going to grow. So we started the top being at -1. So apparently, it is going to be at 0. So that is your first element, 1, continuously, evo, and then because now top will be something, maybe a number like 4. If you remove array at 4, you'll be removing the element that you just entered there. I hope it makes sense. So pick is just, you're not removing anything, you're just looking at what is at the top of a stack. So before I continue with that, anybody who has a question, ama anybody who wants to explain more, haraka. So can I just go on? So I hope you may sync. Kendi?
Iko sawa, endelea.
Okay, thank you. So implementing a stack, uh, no, not queues. Using, okay, I have implementing stacks using, I wanted to show you in Python. I don't know why I don't have that. I don't know, but I find C being difficult for, but I'm going to explain just in case you understand well and good. Python is easy to read whenever you are implementing. So you define a structure. So when you implementing a stack using a linked list, so first of all you create your node. So using struct. So this is how you define your node, and then so this is now you defining now your stack, because for you to implement a stack, it is like a couple of nodes joined to one another. So that is a linked list joined to one another. And then if you pop at the top, now that is where the implementation of a stack comes in. So the first thing, you initialize a stack to null, so that now you create your stack. So you can now check if your stack uh, is null. If the top of the stack is null, then that thing is empty. So you can start adding whatever you have in your stack. So you create a new node, as you do in linked list. You create a memory, you insert data, and then you check first of all if the stack is either full or the memory has been allocated. I mean, in C, you have to check if the memory has been allocated whenever you're creating a new node. If it has been allocated, new node is equals to the data, new node data is equals to value, new node next is equals to stack at the top, and then stack at top is equals to new node. So popping, the same concept again, removing an element now from the start. Whenever you're popping, because you remember we were inserting things from the start, so you have to remove it from the start. That is because the last element you just inserted became the first one, the first element in that linked list. So you remove from that from the start. Any question? Yeah, that is why I hoped to share the thing before showing you the code.
Okay. Nimeona Kendi anasema mambo ya ni tough yawa. So
Mambo ni,
anasema mambo ni tough yawa.
but at least and understand like the whole general concept yenye ninajaribu kuexplain from the graphics.
Beza Kendi unaelewa like apart from the code, yeah? Kama ingekuwa Python, I think it would have been much easier.
Yeah, I don't
But
know. I thought nilikuwa na ya Python. I don't know kwenye ilienda.
but ideally what's happening ni if you get to understand ni kama okay, this is not the best example ya kutumia, but imagine this ni kitu kama chupa ya solid mafuta. Ukiweka mafuta alafu ujaze the bottle na ni solid, eh? Utakuwa ukichukua hii mafuta yenye iko juu kwanza ukichukua. So ideally ukikuja kwa code, what happens ni first, if you're like tukiongelelea nodes, ni node ya kwanza inastakiwa kwa node ya pili, inastakiwa kwa node ya tatu, inastakiwa kwa node up to the nth element. So first, before you make anything, you have to have that node. So you're going to check kama if the node has data ama it's an empty node ama vitu kama hizo. That's ideally what Samson is showing you. Ni vile hakuna ya Python. I think Python ingekuwa simpler. Ni vile for C you have to manipulate the memory a lot by yourself as compared to Python. Sindio Samson?
Yeah, I guess. But I will try to give you a more graphical, a more logical explanation kwa queues, and then we hope like from because queues na stacks ziko na relationships. That is why we're presenting them together. Tutaona kama like you might get something, but still I'll share this in the group, and then unaweza read through, and then uone kama uta understand.
Yeah.
Okay, kiriko na mchezo. For some reason, I can't go to the next slide. Just let me refresh this. Okay, so I think tumefika kwa queues, but I don't know why my computer in a hang. Just let me restart this. Okay, okay. So in queues, so as you remember what we mentioned in queues, you are in a line unaenda super metro. The first person who comes first is the person who is going to be served first. Unlike in stacks, the person who comes last is the person who gets served first. So this is basically the opposite. So what operations can you do in a queue? You can add an element at the back of a queue. So whenever we have queues, we'll have two terminologies: a rear and a front. So a front is tuseme pale kwa super metro, ule mwenye uko karibu kwa mlango, that is the guy at the front, so that is the front. The back ni penye sasa watu nakuja wakipangia laini wakijiongezea, so that is the rear of a stack. So wherever you are adding elements, the point where you are adding that element, that is at the back. Where you are removing them penye wanajisavia, that is at the front. So you can add elements, you can remove an element from the front of a queue. You can retrieve the front element without removing it. So that is basically like pick in the other one. So rear retrieve elements without removing it is empty. You can check if a key is empty. So implementation, you can use linked list, arrays, or stacks, or any other data structure you come across. So this is a basic implementation of queues using arrays. So apparently you have an array. So the first thing I enter is 2. The next thing I enter is 3. The next thing I enter is 4. Go in 5, 6, 7, and 8. So whenever I want to remove, rather than starting by removing 8, also there is a 9. So rather than starting by removing a 9, you start by removing the first element that you entered in that queue. So basically it is the opposite of whatever we had previously. I hope this one is easy to understand. You just remove the element that you entered first. So implementation of a stack of a queue using a linked list. So these are a picture that I thought can communicate, much better. Sage,
Yeah. So
nasikia mtu akiongea, so I thought mtu ako na swali.
yeah, kuna mtu akona swali by the way kwa queues. No one.
Okay, so if hakuna swali, well, I think we can continue. So whenever you are like, you remember what we had with linked list, sindio? So you have your not linked list, stacks. So you are inserting links at the front, and then you pop them from the other side. So the same concept is gonna be applying here. Whenever you're inserting things, you insert them. So okay, for queues, you have to like have two pointers. So one will be pointing at the front, the other one will be pointing at the back. So just to take you back so that I see if you can understand. So you remember when we were talking about linked list. So and you have not linked list. I don't know why I'm confusing myself. When we were talking about stacks, so when we were inputting elements, we used to be like index 0. Let me just go back to that diagram. At index 0, you enter 12, and then you go at index 1, you enter 08. You go to another one, you enter 21, 33, 18, and 40. So apparently, with a queue, so when you start in here, you will have two pointers. One will be like rear, and then the other one will be like the front. So both of them, we should do something like equate them to -1. And then when you enter something, you now increase both of them to 0. And then if you enter another one, the rear one, which will be like the top, you increment to 1. You increment by 1. And then you enter another one by 1, by 1, by 1, where else the one that is at the front remains constant. It doesn't change from 0. So that when you start, like, because when you enter the last one, like the rear will be used to calculate like to go at what position. If you are position 8, we are going to be entering array at position 9, the next one, and then array at position 10, the next one. Now, when we are now dequeuing, we will now start from now this one, because this one is at index 0. We remove this one, and then the whole link list now shifts forward, and then you remove again that one. So that is the whole point of dequeuing. So you can use the same concept in linked list. So you have the back one and the front one. So what happens here is you keep inserting elements at 0 of one time complexity. That is, you insert at the front, and then you keep a loop maybe at the back. Sawa sawa. And then you keep as you're inserting them, you can insert it O of one time complexity, and then you start removing them from the back because you have the counter or from the back. Or you can decide to do the other way around. You insert them from the back, and then you remove them from the front. So when in queues, you can do either way based on whatever you want. Any questions so far? Masharia,
Yeah.
am I losing you ama tuko pamoja?
Mi niko fiti. Anyone amepotea ama
Muva?
anyone who actually need further explanation kwa ajili we can like explain it in the aspect kwa ajili maybe you got confused like sema we can put them from the back and remove from the front.
Muva, sijasikia?
Nafuatilia tu.
Okay, fine. So I believe so far nimewaonyesha like how to do it. So let me go to the code and see if I have queues using linked list, queues using array. So when you inserting queues using array, I decided to use like the simplest way to implement this. You use just an array, and then if you append something in an array, you are entering like at the end of that array. If you pop something from an array, you'll be removing an element from that array from the first one. So you append, you enter at the last one. You pop, you remove from the first one. So ideally that is the basic implementation. So what I did here is you just create an empty array, and then if you want to enqueue, you append an element in that array. If you want to dequeue, you just check if it is empty, and then if it is not empty, you just remove, you pop an item. If you want to pick, you just look at what is at element 0. So when it comes to queues and stacks, so in queues, if you want to pick, you're looking at the one at the front, the one at index 0. In stacks, if you want to pick, you're looking at the one at the top. So basically that is the whole implementation. So that one, I think now we can go to queues using linked list. So yes, so this one I have one for Python. It is a little bit more straightforward. So what you do is you create a node, sawa sawa. So that is a node for linked list. You have the data and the next node, and then you initialize that with front and rear. So you have two pointers, the front one and the rear one. So both of them, you just equate them to null, so to have nothing. So for you to check if it is empty, you just check if empty is none. If front is none. If front is none, that means you've not added anything. So now you can skip that. So enqueue, you just check. So whenever you are enqueuing, you first of all create a node because you want to add a new element to that node. So and then you check if the rear is equals to none. So okay, so if rear is equals to none, so self dot the front one is equals to rear is equals to now the new node that you have created. So you're trying to insert this thing huko mbele. I don't know how to explain that. Sage, do you like the whole concept? You want to insert thing at the front, and then you have another pointer that is looking what is at the back, and then whenever you are entering, you are growing the size of that thing, and then the rear and the front is keeping track of both the size of the queue, and whenever you are popping, you can just shrink it. That is the whole concept. Even when it comes to dequeuing, you just check if it is empty. If it is not empty, you remove the one at the front, and then you decrease. You point the one now you have appended at the front. You point to the next node. That is the whole concept. So this is the code that we have. I have it in my GitHub repository. Sage will post the thing here so that if you have any question, you can go check it. I'm trying to go fast because time is not on our side. So when do you use stacks or queues? So when to use stacks? Uh, when you want to maintain the order of operations, maybe things like undo operations, expression evaluation, things like plus, minus, and then you want to, you see how you do in your calculator, those expressions, plus comes before that, is of it, how they follow each other. Implementing recursive algorithms, if you need to track the history of things that the way they happened, things, using graphs, that one somebody should teach whenever they're teaching graphs. It is very important. So when to use queues, if you want to process things in a queue, most probably zote zinaenda in a queue. If you want things to go in a chronological manner, you use queues. I wanted to just touch on something. I don't know why it may hang. Okay, so implementing a queue using a stack. So ideally, if you want to implement a queue using a stack, so what happens is you're given two stacks. So a stack, you have to remove something from the top each and every time. So I give you two stacks. Sawa sawa. For you to be able to remove, you see, uh, just to point out, in a queue, if I enter something the first one, I have to remove it as the first one. So if I have numbers like 20, I have two numbers in a chronological manner like 1, 2, 3, 4, 5, 6, 7, 8 mpaka 20. The first number nili insert ni 1, 2 hivyo zikifuatana. The first number I will have to remove is 1. And then the last number nitatoa ni 20. So if I have two stacks, so I can take like stack number 1 and stack number 2. So I enter things in stack number 1. So say I put like 1 in stack number 1. Then I put 2, 3, and then 4. sawa sawa. And then for me to be able to remove like one as the first one, I take the other stack, I start putting things, I start removing things from stack number one. So ninaweka 4 3 2 1, sawa sawa. And then if I pop them, you see I'm popping zikiwa zinafuatana. I don't know if you're getting my mental picture. Sage,
Yeah.
are you getting kenye najaribu kusema?
Yeah, nimeelewa the implementation of queues using stacks.
Yeah,
But
so
kuna mtu mwingine mwenye amepotea or something. Kendi, uko sawa? Viva,
okay,
uko fiti?
okay.
Ah,
So
uko sawa. Endelee.
I'm assuming inaenda hivyo. I'm seeing time ndo inasonga mbio. So implementing a stack using a queue. So the idea here is to keep a newly entered element at the front of Q1 so that pop operations dequeue from Q1 to Q2. Sage, unataka kuelezea hii?
The implementation of stacks using queues.
Yeah.
Okay. So the basic idea of this thing, yeah, ni you have to separate queues. Let's take, we'll use the examples you guys are seeing on the slideshow. The front will have Q1 and the rear will have Q2, right? So, like we've seen for stacks, we first take what's what comes in last that will come out first, right? That's for a stack. So since the front is Q1, what's at Q2 will be what's coming out first. Sindio Samson?
Yeah. Uh,
So if we've already enqueued, kama kuna mtu mwenye I think kila mtu anaelewa ku enqueue ni nini. Kama enqueue whatever Q2 was enqueued, then what will be dequeued will be coming from Q1 all the time until
yeah,
Q2 with the rare one ya mwisho kuingia.
yeah, the whole concept ni unajaribu kuzipoanisha Q1 na Q2. I assume iko well understood. So another example nimewaletea ni reversing a string using a stack. So you have a string like Dennis. So you have a string like Dennis. So D, E, whatever is D is at the first, S is at the last. So that is like an array. If you want to reverse that using a stack, so you loop through the word Dennis. So the first element to be entered will be D, E, N, whatever I, S. And then when you are popping, because S is the last element to be entered, now you'll create the string again ikianzia na S, hivyo ikifuatana, and then D will be the last one. So apparently you've reversed a string using a stack. Sindio Sage?
Yep, that's how it happened.
Yeah, so I
And so
assume
if someone pays attention, this can be considered like something interview questions with kama hizo.
yeah. So need some concepts, and I think I am done unless somebody has a question. I didn't think it itaenda hivi long. I thought itakuwa tu like 30 minutes and then iishe.
Oh, alafu kumalizia ya.
Okay, yeah. Anybody mwenye ako na point ama a question you can ask at this juncture.
Okay, KND had said that we can add different types of queues. On that note, I'd like to tell you guys this. First, understand what's a queue, what's a stack, blah blah blah. If you understand this, these concepts are circular, simple, priorities. It doesn't really matter much because they are basically dealing the same concept that's happening for the first queue, the basic one. Sindio Samson?
Yes, but we can cover them like next. Ama if you have a personal question unaweza niuliza, just tag me
Yeah,
in the group and then I will explain that concept to you.
yeah. Anyways, tumemaliza the session. Kuna mtu yote wanted anything, this session itakuwa up on YouTube, and if anything else, yeah, I don't think tunaweza kakuwa na anything.
Nakaa content imekuwa mingi sana, hakuna mtu anaongea, so I think we're going to end at this time. So If
Yes,
nobody has
Samson.
a question tunaweza end hiyo.
Umeulizwa swali
Oh, sijaona.
If it's a circular queue, will it be first in, first out?
Ati, pardon?
If it's a circular queue, will it still be first in, first out?
Okay, so the whole concept of ikiwa circular or not inakuanga like iko ni a queue inaendeleza like in a string, and then to some point iko na a circular thing, sawa sawa. So ideally what you do is sasa hapa ndo the concept of breadth first search inakujanga. So you keep track of like whatever you have visited, and then after you visited that, you now move to the other one, so that if you keep track of what you already visited, that means you will be looking at nimeshai visit, so I cannot visit again, and then if I come and meet it again, so that way I won't pop it. So I think nimeansa swali yake.
I think so. Umelewa
Tebu
nafikiri.
aulize tu swali because I can't see like ni nini kinaendelea, ama let me go to that page.
Eh, finye tu escape hapo penye huko.
Okay, I don't know mbona hii mashini iko moto hivi na alafu inafanya vituko.
Finye escape penye huko kwa ajili niko browser.
It's not like sifinyi. Okay,
Umefinya escape ndio uende kwa Jitsi.
okay, so
Hapo
please
kwa chat.
make sure you stop the recording before. Hii ni nani
Enda
ametumiwa?
kwa chat achana na hizo.
Okay,
Hebu
uh,
niulize Sam swali
uliza
moja.
uliza.
Ona hizi vitu kama hizi data structure sana sana zinakujanga mtu akiimplement hizi systems kubwa kubwa. Na what about hizi systems zenye mtu ana create kama ni maybe a simple website ama a simple blog like hizo ama zimati like huku chini.
See, ina matter based on like what you're implementing, si ndio?
Mm.
Tebu imagine saizi you're building a system, si ndio? It
Mm.
is very small, lakini the whole goal ya hiyo system, si ndio,
Mm.
ni
Mm.
kuqueue watu, ama like tuseme kama saizi you are a content creator, si ndio? You want
Mm.
mwenye ana book session asubuhi hapa akuwe served wa kwanza, si ndio?
Eh,
Si ndio? Yeah, so
yeah.
the way you retrieve hiyo data ni based on kitu kama
Mm.
time ama kitu ingine, si ndio?
Mm.
So if at all would decide wait, hata that is not even a good example. Ushaisikia kitu kama RabbitMQ?
Najua RabbitMQ.
So the whole idea ni inakwanga an asynchronous event emitter ama handler, si ndio?
Eh,
So ile data yenye unasend ya kwanza ama kitu yenye unasend iprocessiwe ya kwanza,
eh,
ndio inaprocessiwa ya kwanza, and then zikienda hivyo as they come through, si ndio? It
eh.
is not a big system but it is a small system na ina work. So I think unazitumianga like anywhere, be it a small system ama a big system, ama unajua like
Tuseme, hebu nikuulize,
uh-huh.
tuseme niko na blog yangu iko na 1 million posts. Si hiyo basically hiyo ni kitu kubwa juu hizo vitu zote ziko kwa database.
eh,
So tuseme nataka okay, tuseme like nikiwa na tuseme hizo 1 million posts naweza implement like ama naweza weka hiyo database aje such that ku retrieve kama ni zile niliweka za kwanza inakuwa very easy.
so hizo ni
Ama
operation.
iwaki hivyo.
Okay, kwa database ni different,
Mm.
lakini unaweza hiyo kitu ya database inaitangwa je, venye ili kuenable like fast querying inaitangwa indexing.
Indexing.
eh so
Ah,
yeah, so ukitumia kitu kama indexing
eh.
based on venye unazi index, unajua sasa zenye zinaingia hivyo zinakuja zikijistack hivyo,
Oh,
so utazi retrieve based on vitu kama hizo. So hizo ni some of the operation, alafu ushaiona like unajibu from one, tuseme kama saizi uko na form, si ndio? Then
eh.
una click inakupeleka next, una click inakupeleka next, una click inakupeleka next, lakini haisave hiyo data immediately kwa database. Like ushai click and then unaona buy na move inakupeleka like step 2, step 3, step 4, step 5.
I do submit.
Exactly, so hizo zote unazistack ukiwa unazisave mahali, then unazisend zote.
Okay, understood.
Okay, so kuna mtu aliuliza swali lakini I didn't get the question and I was looking for it. Candy, naenda
Hello,
naelewa vile.
unanisikia?
Oh yes, nakusikia.
Oh, mi nilikuwa nauliza, mi ndo nilikuwa nauliza hiyo swali ya circular queue. So nilikuwa nashindwa. So umemention ati you can use breadfast search. So I was wondering,
Mhm.
I thought like for you to use breadfast search
Mhm.
it's for nonlinear data structures kama trees.
Ama graphs.
Because I'm a graph, yeah. So how does it work when you're working with a linear data structure like
So
sasa
iko
kama kwenye tunaongelea?
yeah, so itakuwa circular, si ndio? For you to avoid like kwenda in circles, si ndio? See wherever you start. So nilikuwa najaribu kuexplain na concept ya breadth first search, si ndio? Whenever you're searching something, in order for you to not go back to kwenye ulianzia, si ndio? Na ushinde ukienda in circles, penye unaanzia you save that somewhere, si ndio? Like una mark hiyo as visited and then you go all through. If you come back to that, si ndio? Jua umemalizana na hiyo, it's either utafute another place unaweza enda ama you are done with that. Wendy, did I answer your question?
Almost. So what kind of traversal is that? Because I don't really think you can call that breadfast search.
Yeah, it's not breadth first search. Tuseme tu ni psychology, ni akili tunatumia.
Mna overuse akili.
Okay, ni kama okay, ideally this is not the best algorithm naweza kasema inatumika. Ni kama unaonanga vile last session nani Mary alisema tunatumia tortoise and the hare.
Hiyo sessions they watch bado. I
Okay,
was not
so
present.
there's this algorithm inaitwa tortoise and the hare, but purpose ya tortoise and the hare ni kujua kama unarudia like whatever circular whatever in an array whatever you call it, sawa. So tortoise and the hare ni kuna moja ina traverse haraka like let me just tell you what it is, eh? Let's say you have uko na like values, let's say we're having a circular whatever, we have values hapo hivyo, si ndio? So you
Eh,
need to have to you
Mahaj.
need unanisikia? Hello, unanisikia?
Nakusikia nilikuwa naambia Sam ame
Oh.
expose WhatsApp yake.
So for the tortoise and the hare, uh, you have the purpose of it is to traverse na kujua kama the thing it keeps on repeating itself, sawa. So the first one will be moving 2 times faster than the second one, sawa. The first traverse will equal to x ya the first one, so itakuwa inaenda kwa value ya kwanza alafu ina skip value ya pili alafu inaenda kwa hiyo ya tatu ina skip hiyo ya nne, you get the picture, right? Alafu the tortoise sasa inaenda one by one, one by one, one by one, unaona? So hii ya kwenda one by one, this one that has been skipping sitaenda ya mwisho alafu irudi huku kwa ya kwanza, alafu ikirudi kwa ya kwanza basically for the tortoise and the hare ni kufind the middle of a linked list ama si ndio Samson?
So niko na hiyo picture, kuna mali nilituma kwa group yetu ya WhatsApp. Sasa ndo nilikuwa nimefikiria kwenda kuangalia hapa and then nikakumbuka ninashare kila kitu.
Na
Sasa sijui ni stop kushare and then nione hiyo group niichukue and then ni share haraka, si ndio?
iko sawa, iko sawa.
Just 1 minute ni kuexplain hiyo concept Kendi.
Okay, sawa.
Am I sharing?
Saizi ushare.
Okay. Let me, hiyo group inaitangwa ni hapa. Sasa shida ya hapa tunashareanga vitu mingi sana. Hakuna mtu mwenye anakumbukanga ni chats zingine zinapoteleanga.
But then you watu mmeona vile dola imekuwa ikishuka of late.
Si hatuna madola pale.
Hamjakuwa mkifinya kompyuta? Mvu hujafinya kompyuta?
Karibu nirudi ushago.
Hajafinya control for
Nasema chake kuchati hivi sana bwana. Mnafanya link za maana zipotee.
Si utafute kwa nini?
Umeiona?
Kwa images.
Ameiona.
Kwa media.
Okay.
Nimeipata.
So
Kuja
let
share
me
sasa.
share. So
Maana
sasa hii ni circular. Hii ni sasa ndo naambiangwa, si ndio? Finding the start of a loop in a circular linked list. Sawa sawa? The moment mtu amesikia ni a circular linked list, anadhania ni linked list ya circle. But sasa this is how a linked list inakaa, hii circular linked list. Sawa sawa, Kendi? So kuna 1 2 3 and then sasa hapa inafika hapa kwa hii red inaanza kwenda in circles. Si unaona Kenya na share?
naona.
Okay, so for you to determine like the start of that, you know, circular linked list, si ndio? So start ni hapa. Unaona penye imetoka kwa hii linear and then inaingia hapa. Hii ya red ndo start, si ndio? Una create what do you call them? Remind me two whatever yenye anasema fast and slow pointer, si ndio? Sawa sawa, so fast pointer inaenda twice, kenye slow pointer inaenda. Sawa sawa? Okay, fine. So hapa initially inakuonyesha iko na fast na slow na hazijaanza kumove, si ndio? So okay. Nataka kukuonyesha, so ideally uko nayo hapa, si ndio? What
Yeah.
you want to do ni kudetermine like hii point red penye iko. So that is what you want to do.
Yeah.
So the first step ni kudetermine kama hii ni a circular, hii linked list iko na ni a circular linked list. Sawa sawa? So how do you determine it is a circular linked list? Sawa sawa? You move first pointer unaimove twice, slow pointer unaimove once. Sawa sawa? So slow pointer unamove hapa, fast pointer unamove hapa. You get the point?
Okay, yes.
Haya, so ideally sasa sijui kama uta keep track, lakini ndivyo kitaumana hivyo. So slow pointer ikiwa hapa, si ndio? Fast pointer ikiwa hapa, slow pointer iko hapa, si ndio? So juu fast pointer iko hapa, inarika twice inakuja hapa, si ndio?
Okay.
Slow pointer inakuja hapa, si ndio? Sawa?
Hapo ama mali red iko.
Si tumemove mara mbili.
Imemove twice.
Si tumemove
Kendi,
1 2. So
Kendi.
slow pointer
Uko na fast pointer na uko na slow
1
pointer. Fast
2.
pointer skips na slow pointer ina move step moja. So fast ikiendanga, hiyo imeenda ikiendanga. Slow inaenda step moja moja peke yake, you get?
Aya, hebu niambie tena, sorry nimekuwa interrupted kidogo.
Can you
Haya,
repeat?
Samson anakuambia uko na pointers mbili, sawa?
Yes.
First one and a slow one.
Yes.
Ndio ile akakuexplainia. First pointer ikimove kutoka kwa hiyo F iende kwa hiyo slow pointer ikitoka kwa hiyo penye unaona hapo penye S iko.
Yeah. Saizi ama ile ya kwanza?
Saizi. Sasa
Naiona.
hiyo S ni slow tu, sawa?
Yes, I'm slow.
Hiyo S ikisonga moja, first iliruka hiyo penye S inaenda ikaenda kwa the next one. So hiyo first one ina skip, always itakuwa ikiskip, inasonga, haiendi step moja moja.
Posho unaongea hiyo si posho ongea ijaba.
Okay, Sage, move on. Tebu angalia hivi. Acha
Hiyo
nikuonyeshe
part ya
like.
kuruka ndio sielewi, ati naruka ikiendanga.
Okay, tebu angalia hivi move on, si ndio?
Eh.
Acha nikuexplainie like in order for you kupata like hii point ya red, sawa sawa? You first have to determine if this is a circular linked list. Sawa sawa? So how do you determine if this is a circular linked list? Sawa sawa? You do it this way. Unatengeneza 2 pointers, si ndio? Fast na slow. Sawa sawa? Fast ina move twice, slow ina move once. Sawa sawa? Tujaribu
Hivyo ndo mko mmesema.
So kumaanisha
ehe.
first ikikuja point to slow, hiyo ni circular link.
Exactly, hivyo tu.
But so hiyo sasa kusema ikiendanga
Okay, so point ni unaona kama saizi kwa hii example tujaribu sasa kuisolve like venye itasolvika. So nyinyi mjaribu pia ku keep track. Sawa sawa? Haya, first zote mbili ziko hapa, si ndio? First
Okay.
iteration, first pointer ina move hadi hapa. Sawa sawa?
True.
Slow pointer ina move hapa, si ndio?
Correct.
Haya, first pointer iko hapa for now. Second iteration ina skip inakuja hapa, si ndio?
Mm.
Haya, slow pointer inatoka hapa inakuja hapa. Si tuko hiyo ni second?
Yes.
Haya, first pointer iko hapa ina skip inakuja hapa, si ndio?
Mhm.
So the third one slow pointer inakuja hapa, si ndio?
Ndio.
Haya, nini tuko hapa, si ndio?
Ndio.
Haya, tuna skip tunakuja hapa, si ndio?
Yeah.
Slow inakuja hapa, si ndio?
Mm.
Haya, tunatoka hapa tuna skip tunakuja hapa, si ndio?
Mm.
Slow inakuja hapa, si ndio?
Mhm.
Haya, tunatoka hapa tunakuja hapa, si ndio?
Mm.
Slow inakuja hapa, si ndio?
Mm.
Tuko wapi hapa?
First inakuja hapo.
Hapo.
Hapa, si ndio?
Eh.
So zina meet hapa apparently kulingana venye tumecalculate, si ndio?
Yeah.
First ina point to wait, inafaa kuwa first
Aha.
na slow zina point to the same ama first na point to slow, like inazunguka inakuja kuipoint to
Zote zimepatana in the same node.
juu. Nakumbuka Mary akiexplain alisema alipeana example ya like ile kuzunguka uwanja, for example vile mnaanzanga nyinyi wote place moja but like watu wenye wako slow wanazungukwa like tukaa hiyo.
So apparently, si ndio?
Mm.
Venye tumecalculate tuseme zikikuja zimeet at a point. Tumesema zina meet wapi hapa?
Yeah.
Okay. So zikisha meet hapo, si ndio?
Mhm.
Sasa sijuu zimemeet ndio umedetermine hiyo ni ya circular. Sawa sawa?
Wait, so hapa mali zimemeet ndo sasa the starting node ya hiyo
No, no, no,
circular.
no, no, no. Hiyo si the starting node. Hiyo ni
Hiyo ni kudetermine kama
kama
ni
ni
circular.
circular.
Oh.
Haya. So juu umesha determine sasa ni circular. Haya, unakuja sasa unachukua unaacha sasa first pointer ama slow pointer hapa. And then unarudisha pointer moja unarudisha hapa, hiyo nyingine unaacha penye zimepatania. Sawa sawa? And then sasa ili determine penye ile start ya circular list inaanza, sawa sawa? Zote mbili sasa unaanza kuzimove moja moja zote mbili. Sawa sawa? So slow una move once, fast una move once. Hii una move once, hii una move once. Hii una move once, hii una move once. Penye zitakuja kupatania zinafaa zipatanie hapa.
Hapo ndo na determine start.
Sasa hiyo ndo the start point. Sawa sawa? So sinaona kwa hii diagram zimeenda hivyo, sijui kwa nini sisi tulikosea mahali, lakini zote mbili zimekuja zikapatania hapa, si ndio? And then ukachukua moja ukarudisha hapa, and then sasa uka move once na hiyo una move once, 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 and then zinapatania hapa. Ideally zinafaa zipatanie hapo wherever kame.
Right.
Ina make sense, lakini hii example ya watu ni shady sana.
Wewe point ni una understand point, si ime make
Kuelewa
sense. Point ni kuelewa and then uta implement zako. Haya, si tuende hiyo kitu hapo bwana. Hii kitu imeenda, tulikuwa tuende 30 minutes, sasa imeenda 1 hour.
Oh. Nimesahau tena.
Haya, in case mzee ako na swali, I mean,
Unaweza
leo kumekuwa na
kuuliza
turn up mzuri.
Mhm.
So nita save hiyo and then tuta discuss zingine later. But in case kuna still na swali unaweza uliza.
Haya.
Haya,
Sawa. Kesho tunapatana ama kesho ni aje?
kesho
Kesho lazima.
tunapatana.
Sawa sawa. Thank you very much. It was a very nice session.
Okay.